So what I've got happening here is I've got a fast current sensor which I'm outputting to channel B on the scope, and now I've got the scope channel A connected across the blender. So currently the scope is in hold, and what we got happening here is when the PWM turns on, the voltage after the inductor rises slowly, but there's a sharp increase in current. Then as the capacitor in the blender charges, you can see the current come down, and then at that point the PWM has reached full voltage. The cap has stopped charging. Then the PWM turns off, goes the other way, current goes the other way, and then you see the cap charge. Then the current goes back to zero again, and one can see some ring taking place here as well. So what I'm going to do is just show you what the PWM looks like when I go out to 1 millisecond. This is 50 microseconds. So the scale is 200 volts per division, so we're going to 540, which is fairly high voltage over there. So let's put that back and run. I'm going to start the drive, and then we're going to go to a millisecond. Let's go even more, 5 milliseconds, and there you can see the actual sine wave output from the drive, and you can see the current that flows through the current sensor as the drive switches. So that's what the PWM on the output of the drive looks like. So what I want to do is move this to across the inductor, and we'll see what that looks like over there. Look at the voltage across the inductor and then the current at the same time. So I'm going to unplug it, because I need to bring the scope probe across to the inductor, and we need to connect to that. So let's see if we can do that. Let's put the probes down. Let's see if we can get this insulation tape removed. Ow, that inductor's hot. I was running it, and of course the inductor gets hot because we have high frequency going through it, so the reactance goes up. Of course the losses in it go up. Let's cut that off. Some side cutters. Fiddle, fiddle, fiddle. Right, let's see if we can get the scope probe hooked on. So go across it like that. Right, you stay there, scope probes. Let's turn the power back on. And put that back into there. Now we are just seeing a whole lot of PWM. That's at 3 kilohertz. Let's go a little bit faster. So yeah, every time the drive switches, one can see the current. So yeah, there you can see as it switches, the voltage goes up and the current comes up. So that's what it looks like across the inductor. We're currently running a 3 kHz switching frequency on the PWM. Let's make it safe again. What I want to do is connect this to the red wire. So and this over here. Fish out the red wire. Get that connected. So we want to go across that wire and the black wire. That one over there, like so. So we're directly across the output to the VSD now. We're going from black wire to black wire. Get back in. Alright. Turn that back on. So now you can see what the PWM looks like. There's your switching and there's your current. So let's see if we can't look at it a little bit more closely. Let's go out of it again. Okay, so there you can see the drive output switch on. You see the current come up and then decay as the cap charges. And then when it switches off again, you see the current go negative and decay as the cap charges. So that's what's happening on the PWM. Let's have a look at it. In that form. So there we have it. There's our PWM straight out the drive. It looks like that. Okay. That's what you see when you hook a scope directly to the output to the drive. Pulse width modulation, so that's your voltage looking like a sine wave. So your voltage, your pulses get wider and your voltage goes up. Okay. And there we can see the current in response to the switching happening. So if we go back to looking at the voltage across the inductor, we see that it approximates more of a sine wave, because basically this is now acting as an LC filter on the output, a sinusoidal filter. Because it's not set up as an ideal sinusoidal filter, it's not tuned, you're not seeing waveform, a voltage waveform that looks like a nice smooth sine wave, which you'd have if it was a proper sinusoidal filter. But that's what it's looking on the blender side. And then your current passes over here through this transducer. That's your current flowing through the system looks like. So that's what it looks like when we do the current measurement. The difference between before the inductor and after the inductor. Let's fire up the drive again. And there we go. There you can see the it's running at 50 Hertz, so we get into full voltage. So at full voltage there's no switching taking place. Okay. So if I fire it up and turn the frequency down to halfway, 25 Hertz, and we capture that, it looks like that. Okay. So that is now basically your reduced voltage. You can see the pulses start off narrower, get wider, and then go narrower again. And there you can see the effect on the current. Let's go to 2 milliseconds. See if we can see a bit more detail. Alright, there you go. So there you can see it. There's your narrow pulses as the sine wave voltage comes up, and then they get wider. Okay, that's your PWM on the output of the drive. Now if we had just an induction motor connected to the output, this would look different. But because of the radio frequency interference capacitor in the blender, we are seeing sharp current spikes. This is fast. This is a 200 kHz bandwidth, this current transducer over here, and it's isolated. I would put this onto my storage scope, but I need a high voltage channel and I don't have an isolated differential probe with me. That's why we're having to stick with this scope, because it can handle 2 kV and it's got isolated inputs. So despite it being an old scope which I dug out the trash, it's got a cracked screen and a dead battery, it's still very useful. So let's see if we measure the voltage. So it is measuring 170. That's the voltage RMS that it's measuring. So as I bring the frequency down, you can see the RMS voltage coming down. Of course your output frequency and your voltage are dependent. It's a relationship. The voltage comes up as the frequency comes up. That's going out to the motor. You as you turn the frequency down, you see that voltage coming down. That's how AC drives work. You're controlling voltage and frequency, because the motor voltage is dependent on speed, which is a function of the frequency being sent to it, and so on. They're all related. So that's what's going on here. So there we've had some look at the waveforms coming out of here and what's going on, and it's very interesting. And I think we're going to wrap it up at this stage. This is a continuation of yesterday's video, some more interesting content, a bit more scope content, and look at current waveforms and that sort of stuff. Hope you find it interesting, ladies and gentlemen. So always it's an interesting video, and it's a pleasure to have you here. So Thanks for being here today. Take care, and I'll see you next time for more good stuff, stories and interesting content. Cheers.